We've solved every major challenge of space travel: navigation, propulsion, life support. But there's one problem we still can't beat. You can't see it, you can't touch it, and it's powerful enough to end every mission to Mars before it begins. Cosmic radiation. The moment we look past the Kuiper belt, past the outer planets, and past the region of our sun's magnetic influence, we enter an unfiltered cosmic shooting range. The greatest danger comes from galactic cosmic rays, or GCRs. These particles are not gentle beams of light. They are the atomic nuclei of elements that have been accelerated to immense speeds by the most violent processes known in the universe. To grasp this threat, you must first understand its origins. Where do these particles come from? They are born from the deaths of massive stars and the feeding of cosmic giants. Specifically, stellar explosions called supernovae are major factories for creating cosmic rays. When a massive star dies, its core collapses, initiating a massive blast wave. This blast wave tears through the star's outer layers, accelerating matter and creating new heavy elements, which are then ejected into the cosmos at incredible speeds, forming the debris fields known as supernova remnants. These accelerating particles are the cosmic rays we detect. Another major source of these hyper-energetic particles comes from the immense power systems of black holes. When supermassive black holes devour surrounding gas in what's called an accretion disk, they shoot out jets of ionized matter, known as relativistic jets, which travel close to the speed of light. These jets, which can extend for millions of light years, are streams of charged particles, including atomic nuclei, that contribute to the cosmic ray population. So, we are talking about two classes of enemies: the cumulative, slow bombardment of GCRs born from galactic violence, and the highly concentrated, energetic bursts that come from solar flares, which also pose a massive threat to human life and electronics in space. Our modern era of space travel has taught us that Earth's natural defenses are the only reason we survive the constant cosmic assault. For millions of years, life on Earth has been protected by the Earth's own magnetic field, which deflects most of these charged particles. When astronauts leave the protection of this bubble, whether to go to the moon or eventually beyond, they are exposing themselves to an environment where that invisible threat can cause irreparable harm, both to their bodies and the electronic brains of their spacecraft. The International Space Station, for example, orbits safely within low Earth orbit, typically about 250 miles above the surface. Even at this relatively low altitude, radiation poses a serious concern, but astronauts still benefit from a significant layer of atmospheric protection and some shielding from the Earth's magnetic field. The true danger appears when we travel into deep space, far beyond Earth's magnetic safety net. This is where the long-term destructive power of GCRs becomes the single most complex physics problem we have to solve. The immense threat of space radiation begins with the most energetic phenomena in the universe. Specifically, stellar explosions called supernovae are major factories for creating cosmic rays. When a massive star dies, its dense iron core collapses gravitationally. The internal density increases so rapidly that the nuclei are physically pressed together, achieving nuclear density in a fraction of a second. This collapse generates a shockwave that should rebound and explode the star, but early computer simulations showed the shock often stalled due to catastrophic energy loss. It took decades of theoretical work to realize that the explosion is fundamentally driven by neutrinos, tiny, weakly interacting particles generated profusely during the core collapse. These neutrinos deposit a minuscule amount of heat just behind the stalled shock, reviving it and turning the implosion into the spectacular, asymmetric supernova explosion that manufactures and ejects elements heavier than iron into the galaxy. The massive energy released during this collapse, about 1053 ergs, which is equivalent to the binding energy of the resulting neutron star, is mostly carried away by these neutrinos, confirming their power. However, the remnant core left behind, whether a dense neutron star or a black hole, is also an accelerator. The immense asymmetry of the explosion, caused by factors like Rayleigh-Taylor instabilities in the neutrino-driven shock region, ensures that the resulting debris is not uniform. This violent, asymmetric expulsion is what helps accelerate the atomic nuclei that become the high-energy galactic cosmic rays, or GCRs. These nuclei are the raw materials of space. The early universe started primarily with hydrogen and helium from the Big Bang. Stars like our Sun are the factories for lighter elements, but supernovae are responsible for making every element heavier than helium and most elements heavier than iron, including the oxygen we breathe and the iron in our blood. These newly forged heavy elements are blasted out at thousands of kilometers per second, moving at almost 3% of the speed of light. Once launched, they roam the galaxy until something accelerates them further, often through collision with powerful magnetic fields, turning them into the highest energy cosmic rays we observe. The speed of these particles is staggering. Another major source of these hyper-energetic particles comes from the immense power systems of black holes. When supermassive black holes devour surrounding gas, the matter spirals inward in an accretion disk. This process releases vast gravitational potential energy, up to 40% efficiency for a spinning black hole, far more efficient than nuclear fusion in stars, which is less than 1% efficient. The enormous magnetic fields generated by this swirling plasma are twisted by the black hole's rotation, funneling the charged particles away from the poles and launching them as highly collimated, near-light speed streams known as relativistic jets. When these streams interact with the interstellar medium, they smash into background material, creating shockwaves and further contributing to the relentless background of cosmic radiation. Astronauts are traveling directly into the exhaust of the universe's most destructive engines. To understand the radiation problem, we must appreciate the environment we live in and the protection it provides. Our entire solar system exists inside a magnetic bubble called the heliosphere. This massive bubble is generated by the Sun's magnetic fields and the solar wind, pushing back against the interstellar medium. It is this invisible bubble that keeps out most dangerous cosmic rays and other particles streaming through space. Without the heliosphere, life on Earth would have certainly evolved differently, or maybe not at all. Within the heliosphere, Earth itself offers two layers of defense. The first is our planet's intrinsic magnetic field. This giant magnetic barrier deflects the majority of the GCRS and charged particles away from the surface. The second layer is the atmosphere. Even in low Earth orbit, where the International Space Station resides, astronauts are still below some protective layers of the atmosphere. The ISS orbits at an average altitude of about 250 miles above the surface, within the LEO limit of 1,200 miles. While astronauts here still experience exposure that causes health concern, they are significantly safer than they would be in deep space because they remain largely within the magnetic field's primary protection. The challenge begins when we leave this safety zone. As space travelers journey toward any destination further than the Moon, they must pass through the boundary of the heliosphere, which ends around 11 billion miles from the Sun. This interstellar space border marks the point where the solar wind weakens and gives way to the interstellar medium. It took the Voyager 1 spacecraft over 30 years to reach this boundary after its launch in 1977. Beyond that point, the high-energy GCRs are virtually unfiltered. Radiation exposure is not a constant threat. It varies with the activity of the Sun. Solar events, such as coronal mass ejections, can cause a sudden, massive increase in particle radiation, called a solar particle event. These events are notoriously hard to predict and can expose astronauts to dangerous doses in a very short time. For astronauts on the ISS, Mission Control can track these events and sometimes recommend protective measures, like sheltering in the reinforced core of the station or inside their Soyuz/Dragon vehicles. However, for a crew on a long-duration deep space mission, like the one contemplated for the Moon or Mars, CMEs pose a near-fatal threat. During the trip, astronauts are exposed to a cumulative dose of GCRs. These GCRs are particularly dangerous because they are heavy atomic nuclei moving at incredible speeds. When these heavy charged particles hit a human body or spacecraft, they cause a cascading effect of secondary radiation inside the vessel, penetrating deep into tissues and electronic components. It's essentially unavoidable exposure. The severity of the risk means that human health and safety is a mandatory focus of all planning related to long-duration space travel. The necessary long duration of deep space missions, which can last many months or years just in transit, means the total exposure time is high. Any future space travel architecture must design around this fundamental physics problem. When the invisible bullets of cosmic radiation penetrate the hull of a spacecraft, they unleash a microscopic war on the human body. The fundamental health risk to astronauts exposed to deep space is the damage caused to human tissues, specifically the musculoskeletal and neurological systems. Cosmic radiation causes damage at the most basic level, the cellular nuclei. When a GCR slams into a cell, the sheer energy of the particle can shatter the nucleus, causing immediate and irreparable DNA damage. While our bodies are generally robust, the accumulation of this damage dramatically increases the probability of long-term health issues, most notably cancer. Scientists are studying these effects intently because the risk profile associated with prolonged exposure to GCRS is a primary limiting factor for space travel duration. Astronauts already face severe physiological challenges in the microgravity environment, even without heavy GCR exposure. Prolonged weightlessness mimics the process of aging and disease on Earth. For example, studies confirm that crew members suffer severe muscle atrophy and a loss of bone mineral density. To counteract the physical changes of microgravity, astronauts must exercise for at least 2 hours a day. Even with this demanding schedule, the physiological effects are significant. The core goal of research conducted on platforms like the International Space Station is to characterize how severe these changes are and whether they can be reversed. The added variable of cumulative radiation dose complicates this entirely. The damage inflicted by GCRs is cumulative, meaning the longer the exposure time, the higher the overall risk of genetic mutation and subsequent cancer. Research focuses on finding treatments for radiation-induced cell damage that can be used to mitigate risks during long-duration voyages. Missions such as SpaceX CRS-6 cargo resupply missions carried science payloads aimed at understanding how to counteract microgravity-induced cell damage in bones and seeking possible treatments for conditions like osteoporosis and muscle wasting. Similarly, experiments test whether synthetic muscle, an electroactive polymer for robotics and prosthetics, can withstand the rigors of space. The ability of materials to resist radiation is constantly being tested, as the machinery must function reliably, especially for high-risk robotic operations. The radiation threat is also linked to the problem of fluid shift in the body. More than half of American astronauts experience vision changes during and after long-duration spaceflight. It is hypothesized that the absence of gravity causes a headward fluid shift. Fluids move from the lower body toward the head, leading to increased pressure in the brain that may push on the back of the eye and cause structural changes. Radiation exposure, particularly during large solar events, could potentially exacerbate this neurological pressure issue. The physiological effects of the space environment are intertwined, forcing scientists to study the effects on the musculoskeletal and neurological systems together. The environment of deep space radiation is hazardous not only to biological systems, but also to the complex technology required for survival. High-energy GCR particles pose a constant threat to spacecraft electronics, causing unpredictable failures in critical systems like advanced avionics. Engineers must employ specialized techniques like dual fault-tolerant computing to build redundancy into every critical component. But the threat of single-event upsets, where one particle flips a bit of memory, is persistent. Research must focus on improving the durability and function of radiation-hardened components to ensure the reliable performance of robotic explorers and human habitats. The straightforward physical solution to radiation is mass, placing enough material between the source of radiation and the target to stop the particles. This is why the structure of the International Space Station uses a specialized protection known as the Whipple Shield. The Whipple Shield is not a solid wall, but a layered, bulletproof vest. It consists of thin sheets of aluminum and layers of woven material like Kevlar and Nexel, designed to break up incoming micrometeoroids and tiny orbital debris. When a high-speed particle hits the outer wall, it is pulverized, and the fragments lose energy as they hit subsequent layers, preventing penetration of the main hull. While effective against high-speed space junk, this passive shielding is insufficient against the sheer penetrating power of high-energy GCRs. For long-duration space travel, the physics of protection quickly runs into an insurmountable logistical problem: the mass penalty. Every kilogram of material that is required for shielding must be launched from Earth, incurring enormous cost and requiring massive amounts of propellant. This makes simply launching huge walls of lead or aluminum economically and physically impossible for deep space journeys. This is why material transport is expensive. For example, the cost of each mission to resupply the ISS is nearly $200 million, and transporting a single pound of weight is extremely costly. If we look at potential future deep space vehicles such as Starship, which has a projected cargo capacity of 100 metric tons, the majority of that mass is required for habitat and resources. Dedicating too much of that capacity to radiation shielding alone dramatically compromises the mission's ability to carry fuel, life support, and critical hardware. The massive power of cosmic acceleration, as seen in black hole accretion, highlights the challenge of overcoming these energy problems. Black hole accretion is vastly more efficient at converting gravitational energy into light than human-made systems. While nuclear fusion in stars is less than 1% efficient in converting mass to energy, accretion onto a black hole can reach up to 40% efficiency. This extreme efficiency confirms that the universe's natural energy sources far outstrip our current technology, forcing us to rely on careful material science rather than sheer power to shield ourselves. The only way to achieve sufficient radiation mitigation while minimizing mass is through strategic resource use, such as using dense, locally available materials like water ice or regolith for shielding once the destination is reached. However, during the months-long transit phase, astronauts remain vulnerable to the cumulative effects of GCRS. The true hidden enemy of space travel is time itself, because time equals exposure. If we could move faster than current propulsion allows, the radiation problem would shrink, but we are bound by the ultimate physical law, the speed of light. The speed of light is the absolute maximum speed anything in the universe can travel. This limit means that every long-duration mission, whether months to the near planets or decades to the edge of the solar system, results in cumulative exposure to GCRs. The quest to bypass this limit is the quest for faster travel, perhaps reaching a fraction of the speed of light. The Breakthrough Starshot project is one conceptual answer, proposing tiny robotic probes accelerated by immense laser arrays to 20% of the speed of light. At this speed, interstellar travel to the nearest star system, Alpha Centauri, could take about 22 years. However, this kind of system is designed for light probes, not massive human-rated spacecraft, which require stability and massive energy consumption to accelerate. Because conventional speed is limited, much of the most valuable information about the extreme physics that generates cosmic rays comes not from light, but from indirect signals. Astronomers rely on multi-messenger astronomy, combining data from different sources: light, particles, and gravitational waves. Neutrino astronomy, which began with the detection of neutrinos from supernova 1987A, is a crucial tool. Neutrinos are particles that interact so weakly with matter that they carry information unscathed from the core of the supernova explosion, a region that is completely opaque to light. Detecting these neutrinos allows physicists to study the explosion mechanism, the physics of the neutron star core, and the energy transfer that accelerates the very particles we fear. Similarly, the search for gravitational waves, ripples in the fabric of space and time, confirms the violence that seeds the cosmos with radiation. Gravitational waves are generated by the bulk movement of massive objects, like the highly asymmetric collapse of a supernova core, or the collision and merger of two black holes. LIGO, the Laser Interferometer Gravitational Wave Observatory, detects these waves. The energy released when two black holes merge can be equivalent to annihilating 3 solar masses of energy into pure gravitational radiation in a fraction of a second. These events are the definition of cosmic chaos, producing the gravitational shockwaves that accompany the particles threatening our existence. The goal of radiation study is simple: to create a comprehensive understanding of the space environment so that we can design a habitat that can survive the universe's inherent hostility. Whether the answer lies in advanced shielding materials or breakthroughs in propulsion, the long duration of space missions ensures that every astronaut is exposed to the cumulative effects of galactic violence. The necessity of long-duration missions is forced upon us by the orbital mechanics of our solar system. We have to wait for the universe to align itself to permit travel. If you are interested in exactly why these missions take so long and the surprising mechanics that dictate the actual transit times, click here to watch real time it takes to get to each planet video. I'll see you there.